our memory. We added and subtracted matrices from each other, and in order to do that, they had to have the same dimensions. And we multiplied a scalar by a matrix, which was just taking a number and multiplying it by every element in the matrix. Multiplying two matrices is a bit more involved than that. So first of all, remember that in order to add or subtract matrices, they had to have the same dimensions. In order to multiply two matrices, they don't necessarily have to have the same dimensions. In fact, sometimes when we have two matrices of the same dimensions, you can't multiply them together, because what you need is for the number of columns in the first to equal the number of rows in the second. And so in this schematic that we have on the screen, what they're trying to describe is they're describing the multiplication in terms of the result. Okay, so this result is, notice, the sum of all of these products of everything in this row times everything in this column. And so in example 1, part A, if I want to multiply A times B, we'll first realize A is 2 by 3, and so is this. So the number of columns and rows this way aren't the same, and they're not the same this way either, which means I can't. This is not possible. Matrix A is a 2 by 3 matrix. Matrix B is a 3 by 2 matrix, which means both products are possible. So here we go in part B. I'm going to multiply A times B. So that means that my resulting matrix will be 2 by 2. And what I'm doing is taking the elements in this row and multiplying them by the elements in this row and adding as I go. So negative 2 times 2 plus 0 times negative 1 plus 3 times 9, which gives me 23. Next, I'm going to multiply the elements in that row by the elements in this column. So negative 2 times 0 plus 0 times 0 plus 3 times 3, which is 9. Next, I'm multiplying the elements in the row in A times the column in B. So 5 times 2 plus negative 7 times negative 1 plus 1 times 9. Finally, 5 times 0 plus negative 7 times 0 plus 1 times 3. So there's A times B. Now I'm going to do B times A, which I hope that you'd realize is going to end up being a 3 by 3 matrix. So in the interest of being really clear, I'm going to write them in the order in which I'm multiplying them. So I'm multiplying 2, 0, negative, whoops. 2, 0, negative 1, 0, 9, and 3 times negative 2, 0, 3, 5, negative 7, 1. I'm multiplying in this order. So again, I'm going to be multiplying what's in this box times what's in that one. So negative 2 times 2 plus 5 times 0, that's negative 4. Next, I'm multiplying the first row of the first matrix times the second column of the second matrix. So 2 times 0 is 0, 0 times negative 7 is 0, and those two things added together is 0. Next, 2 times 3 is 6, plus 0 times 1 is 0, so that's 6. Next row, negative 1 times 2 plus 0 times 5. So that's negative 2. Negative 1 times 0 is 0. 0 times negative 7 is 0. So I've got another 0 here. Next column. Negative 1 times 3 is negative 3. Plus 0 times 1, which is giving me negative 3 here. Nine times negative 2 plus 3 times 5 is negative 3. 9 times 0 plus 3 times negative 7, negative 21. Finally, 9 times 3 plus 3 times 1. And there's the product of those two matrices. So a couple of properties that do hold true for matrix multiplication, since you may have observed that the commutative property does not hold true. Recall from algebra that there was a multiplicative identity property that said if I take a number and multiply it by 1, I just end up with that same number. And so in matrices, we have what we call the identity matrix. And it is very reminiscent of the row echelon, reduced row echelon form of a matrix. And we can use the identity matrix in order to find the inverse of a square matrix. So we're asked to determine whether these are inverse matrices. So I just said if I multiply them together and I get the identity matrix, then they are inverses of each other. So what is AB? It is the product of these being multiplied by these. So negative 4 times 2 is negative 8 plus 9, which is 3 times 3. Negative 8 plus 9 is 1. And I'm just going to type the numbers into the calculator as I go, because otherwise it's way too dizzy. 3, whoops, I'm moving this. 4 times, negative 4, excuse me, times 3, plus 3 times 4, well, that looks good. Three times 2 plus negative 2 times 3. Three times 3 plus negative 2 times 4. That looks good. I also want to double check in the opposite order. So I'm going to be multiplying these rows by these columns. Negative 4 times 2 plus 3 times 3. Two times 3 plus 3 times negative 2. Three times negative 4 plus 3 times 4. Three times 3 plus 4 times negative 2. So that's yes. How about part B? Six times 1 plus 2 times negative 2. And right away, I don't have to go any further. This is no. If a matrix has an inverse, we say that it is invertible, or we say that it is non-singular. So a singular matrix would have no inverse. And another way, or a way to find the inverse of a matrix is to use systems of equations like we did in lesson 1 and solve that matrix.